Alright, so here we go again. This time we're doing optimizing functions. And you'll understand the name once I get towards the end of this program. So, like it when programs get a little more involved. Teaching these things are a little more fun now that we actually have to think a little bit. Anyways, here are our functions that we declare: compute factorials and factorials int. And it's actually better we do the main function last. So why don't go ahead and get these sub functions, I guess you can call it, out of the way. So here we have compute factorials, and in compute factorials we'll put the first integer in there and then the int max in there. And this is where I should actually throw in the statement for the main function to make this, to tie this. Nope, that was a bad paste. Let me try again. Mistakes happen. Alright, compute factorial. So these are the actual integers that we'll input into this function. 1 and 8. 1 will be int num, 8 will be the int max. And this will be a basic string where it'll start displaying our first number 1, then colon, and then after that we'll have a factorial. We call the factorial from the function below, which we'll get to. Factorials look like this from math: 4 exclamation mark, which will translate into 1 times 2 times 3 times 4, making 24, for example. The incrementer will increase num by 1. Now, if num ever becomes bigger than max, we'll exit the program, and return 0 will do so. Otherwise, else, it will do compute factorials num max, which is the same thing itself. This is it performing itself. Again, is also known as recursive functions, which kind of resembles while loops in a way, but a little different, I guess you can say. And what is that below function? Well, this is what it's going to be. So factorial, as we declared above, will take num variable as it's a passed argument down here. So first there'll be 1, it'll increment to become 2, and it'll do a little bit of math here. Here we did an if statement so that we get some coherent math going on. If n equals 1, the result equals 1, so it doesn't end up being 0, which is false mathematically. As below here, if we were to try to equate 1, it would be 1 minus 1 equals 0, and then it will all fall apart. However, with the following numbers, 2, 3, and 4, due to the increment, and then n minus 1, it'll start adding up with this factorial math. What it's going to do with 2, 3, 4, with this else statement, it's going to start looking like this. It's going to start looking like 1 because 2 minus 1 equals 1, and then the factorial will make it exclamation mark times 2 because it's 2. Then when it becomes 3, 3 minus 1 will then become 2 times 3, and so on. Yeah, it took a little bit of thinking for me to explain it this way because it didn't, but I like saying factorial with the exclamation mark as I'm familiar with in math rather than factorial rather than this format, which is kind of awkward. And basically with this, it'll give us some interesting results. So 1, obviously, because of this if statement forcing the result to be 1. Then 2, because mathematically this becomes 1 times 2 equals 2. Then factorial of this would become 2, and 2 times 3 equals 6. Then we fall to this factorial right here, where 3 factorial becomes 6, and 6 times 4 equals 24. Then so on, then it's 24 times 5. Basically, it's just math here from here on, if you understand it well. The next thing I want to show is where optimization finally comes into play. Meaning we can do the same code, but with different terms. So let's go ahead and kill this code above here and use this as an alternative. Now we're using ternaries, where we test for a true and a false condition becomes 1 if it's equals to 1, else it'll do this. Because we're using this ternary, an if else isn't needed anymore, because it's effectively doing the same thing but in more compact code. Same results, and this I did evaluate to be mathematically correct, so that's all good. So cool. That's basically it.